Right. So, today we're going to start talking about... Whoa, how come it's showing that? Yeah, I know. It does that for the media site videos, but I've never... Might have to go get John here. There we go. Okay. So, Thursday we introduced 5.1, which was basically just a few definitions, and then 5.2 had to deal with the uniform probability distribution, right? Remember, the uniform distribution is where everything has an equal chance to be selected, right? The probability is the same across the interval, whatever the interval happens to be. So any random variable within the given interval has an equal probability of being selected. And then we had a homework assignment about this. Is there any questions about the homework from 5.2? That's due tonight by midnight. It's really a pretty straightforward section. The uniform distribution section is probably one of the simplest that we have in the entire textbook. All right, it's pretty straightforward. Here's an example of a uniform probability distribution. Notice the frequency of every value within the interval is the same, right? And when we multiply the base times the height, we always get 1, which is the area of the rectangle. This is important because we're going to use this rule that the area is 1 when we get to our normal distribution. All right, so this is talking about uniform. Let me zoom it in just a little more. So uniform means equally likely outcomes over their range of possible values. Right? So any value within the range has an equally likely chance of it happening or of it occurring. A good way to think about it, even though it's a discrete probability distribution, is rolling one die. Right? Each of the 6 numbers, if I did it 1,000,000 times, each of the 6 numbers would basically be the same, right? It would be a uniform distribution. The probability that I get any one of the 6 numbers is the same. The outcomes are equally likely. All right? And there's a formula down here at the bottom of this page for it. Where's the next page? What are the formulas for that? Because I want to hit them again. 227. So if you weren't here Friday, you can write these down. Here is the PDF, the function that produces our uniform distribution is simply 1 divided by the endpoints. This is just the range, right? It's the biggest minus the smallest. So it's 1 over the range. The mean is C plus D over 2, which is just the average of the 2 endpoints, right? It's like finding the median of the smallest point and the biggest point. So the mean and the median are always the same when we're talking about a uniform distribution. All right? You'll notice it'll be the same for our normal distributions as well. A uniform distribution is symmetric. Right? If I cut it in half, it has the same thing on the left side as it does on the right side. And then our standard deviation, notice it doesn't give us the variance here. It doesn't give us sigma squared, it just gives us sigma. And sigma happens to be the difference between the biggest point and the smallest point, or the range, right? Isn't that just the range? The difference between max minus min? Divided by square root of 12. Square root of 12 comes from a derivation of this function right here. So just know that that's in the formula, square root of 12. All right? It's not important really where it came from. Okay? So that's the stuff that's due tonight, is the uniform probability distribution. You'll notice X can assume any value between C and D. There are an infinite number of values between C and D. We aren't listing out the values X can assume with commas like we did in the discrete stuff. Right? There are an infinite amount of values here, not a countable amount of values. Right? Yeah, sure.
Standard deviation, I was putting that in the calculator, and I'm getting an odd answer back. So, like...
So D and C are your endpoints. So this is the biggest value it can be, and this is the smallest, okay? So let's go look at a homework assignment and try it. Because it might, it's probably a rounding issue. more than likely, because square root of 12 is irrational. It's a decimal that never repeats and never truncates, right? It just goes on forever like pi.
See, and my answer is coming up with, like, if I do 11 minus 7, it's 4.
So 4 over square root of 12?
Square root of 12.
Should be 2 over root 3, which will be about, what, 1.7 or so?
So is there a way that you enter that in the calculator where the 1.7 comes up? Because I'm actually getting...
Oh, no,
square root
you
3.
probably need to hit what's called the fraction to decimal button. Yeah, you probably have a button on here that changes back and forth. Right here. Second. That's it. Just takes it from a fraction to a decimal.
Thanks.
Because the fraction is much more exact than the decimal, right? So that's why they do it that way. But that's a normal thing. So what had happened with Crystal is she put the fraction in her calculator and her fraction wouldn't change over to a fraction. Or her fraction wouldn't change over to a decimal. Let me kind of show you what's going on here. So let me just do exactly what we talked about right there, because this is a good place to talk about that, especially in this normal section, because we're going to get a lot of decimals, a lot of this type of stuff that we're going to have to worry about. Oh, that's the DVD. Here we go. Okay. Hit the autofocus. All right, so we did, what was it, 4 divided by, see, and my calculator might already be in that setting. Oh, it's because I have that. So it just gives me the fraction. What they've done here, you're thinking, well, how the heck is 4 divided by square root of 12 equal to 2 square root of 3 over 3? Well, what they do is they simplify that radical. All right, so this is a good place to actually talk about this, because we're going to see it a little bit more. So let me show how this equals this, because I know those are some of the scales we really need a little bit of extra practice on, and then show how to make that a decimal. All right? So sigma, what was it, 11 minus 7 over square root of 12? This is just some made-up problem from the homework, all right, where she had the data for it. So this is equal to 4 over root 12. And I'm sure everybody can get to here, all right? That's the easy part. But what we need to do is look in 12 right here. Is there what two numbers multiply to get 12, and one of them is a perfect square? Do we know? What are all the factors of 12? 4 and 3, right? Okay, so this is equal to 4 divided by the square root of 4 times 3, which is legal. I can put a product in here. Now, I can't put 4 plus 3 and have this be 7. That's not true in radicals, all right? Just in multiplication. So here, this is like two split radicals, all right? This is like equal to 4 divided by the square root of 4 times the square root of 3. So this and this are equal. What's the square root of 4? 2. So this is equal to 4 divided by 2 times the square root of 3. What is 4 divided by 2? What is 4 halves equal to? 2. So this piece right here is going to simplify to 2, but I still have my square root of 3 in the denominator, right? So they get to 2 over root 3, which I use this number to come up with about 1.7, right? Because I know this is about 1.7, 1.8, something like that. It's not quite 2. So what they do here, the way they make this look like this is they do what's called rationalizing the denominator. All right, that's not something we're going to worry about, but I want to make you guys aware of how they came up with that. Because looking at it, just glancing at it, it doesn't look like those two things would be equal, right? But they are. And the way they do it is they multiply the bottom by the square root of 3, but whatever they do to the bottom, they have to do to the top. So all I'm doing is multiplying this fraction by 1. Square root of 3 over square root of 3. Root 3 times root 3 is simply just 3, right? It's the square root of 9. So this becomes 2 square root of 3. The stuff in the numerator stays there. Square root of 3 times square root of 3 is actually the square root of 9, which is 3. So that's how they come up with that fraction, right? And this is algebra right here, right? This isn't statistics. What's important is that you can punch that in your calculator and get the decimal. But I want to show the stuff in between. Okay. Now, how do I get the decimal from this fraction? What you do, see this little F to D right here? And all your calculators will have this button. This means fraction to decimal or vice versa, decimal to fraction. So all I'm going to do is hit the second command, hit fraction to decimal, and notice it pulls whatever my previous result is and puts it here. So it says, I'm going to translate this from a fraction to a decimal, and then hit enter. And there it is. So I said 1.7, I meant 1.17 was what my guess was. But, so that's how we do it. So that's how they get this to get 4 over square root of 12 to equal 2 times root 3 over 3. Even in our algebra classes, we've stopped doing this rationalization here. We don't even show that in college algebra anymore, right? Because computers do that for us. And the only reason we used to care about square roots being in the denominator was it was bad etiquette. That's it. Now we don't really care about that, all right? Because computers do it for us. The math's not done by hand like it used to be. But there's the answer. So the standard deviation of this uniform distribution from 11 to 7, which I could go ahead and draw now, right? So here's 7, here's 11. Whoa, I made 11 right there. There's 11. What's the height of it? Do we remember from that page? What's the height of our uniform distribution? And of course I've killed it. What was it to get the f of x value? What was f of x equal to?
Be 1 over 11 over 7.
Right.
11 minus 7.
11 minus 7. 1 over the range. Right here. Which it's easier to see from the graph. The height is 1 over d minus c. Okay, 1 over d minus c. So just 1 over the range. Here the range is 4. Hell, I've already calculated the range. So my height is 1/4, and here's my distribution. There it is. That's the graph. This is f of x. This is x. What this means is my probability that x will assume any value between 7 and 11 is 1/4. All right? And every value in that interval has the equally likely opportunity to be selected. What's the mean of this distribution? Right, we add them together, divide by 2. 11 plus 7 is 8. So that means my mu is 9. With the standard deviation of 1.15. Okay? And the way I came up with 9 is at the bottom of this page, right? It says right here, my mean is always c plus d over 2. So 7 plus 11 is 18, divided by 2 is 9. Which is easy to see what the mean is there. I mean, it falls directly in between. Since 7's odd and 11's odd, it's the odd number in between them. Okay? So there's kind of a review of what we talked about on Thursday. So get in there, play with it, practice it. Really, the only thing in this whole section that's kind of like I've waved my hand at is this square root of 12 in the denominator. All right? You just have to trust why that is. Okay? For the standard deviation. It's always square root of 12. And rather than put the decimal, because the decimal is not exact, right? Square root of 12 is an irrational number. Now I type square root of 12, it tells me 2 root 3, but then I could go fraction to decimal, and it won't even do it. Maybe if I did 2 times second square root of 3.0. There we go. There's kind of a trick, too, to trick your calculator into giving you a decimal. Write this as what's called a floating point number. See how that's not any different? Because when I just type 3, the calculator interprets it as an integer. If I type 3.0, it interprets it as a real number. So it gives me back my answer as a real number. So there's another way to trick the calculator. So this is what square root of 12 is. Notice how this never repeats. Right? It goes on forever. It's an irrational number. All right, so some calculator tricks here on how to work it. Yeah, if you ever do something in Excel, for your classes later on and you want the decimal value, use that little trick right there. Rather than type 3, put 3.0 and return a decimal rather than the fraction. All right? Okay, so let's get into the new stuff. The book was from the homework assignment, so it killed both of them. So let's go start on 5.3. I kind of barely started talking about it on Thursday. The normal distribution. Basically, the rest of this course will center around this normal distribution. All right? All the hypothesis testing we do, the z-score calculations, the t-table, the f-table, all these different tables we're going to eventually see basically come from this section. All right? So the normal distribution, or the symmetric bell-shaped curve, is very, very important. All right? Extremely important. Okay. One of the most commonly observed continuous random variables is a bell-shaped distribution or bell curve, where the mean is the most likely occurrence, and as you move away from the mean, the things tend to be less and less frequent. All right? Lots of things in the natural world assume this probability, or this distribution, this probability distribution. Height, weight, IQ, all right? A lot of different things center around this. Battery life of a cell phone is normally distributed. Right? If you have it at 100%, most of the time it's going to last, 8 to 10 hours. It really depends on usage. Sometimes it'll last less, sometimes it'll last more. Most times it's going to last right about 10 hours or 12 hours, whatever your phone happens to be. So we see this a lot in the real world. This is basically, this type of curve is how they determine who's what they call gifted or above average and who is a below average student, right, or special needs, is from this bell curve, right? 100 IQ, 110 is about mean. If you're about 140 or above, you're up here. If you're below a 70, then you're down there, all right? That's kind of, way back in the, I'm sure everybody in here has seen Forrest Gump at one time in their life, right? And when his mom goes into the office at the beginning of the movie and the principal's explaining, here's average and here's where a forest is. That was a normal distribution. Now, it wasn't shaped in this type of curve. I think it was like more of a chart, but it's the same thing. All right? So right there in the movie, they talked about this exact same thing. All right. The normal distribution plays a very important role in the science of statistical inference. So the science of inferring what's going to happen in the future using data. That's what that means. All right? What's going to happen in the future based on what's happened in the past. Moreover, many phenomena generate random variables with probability distributions that are very well approximated. So a lot of things aren't exactly normal, but they're very close. Here's a bunch of examples. Blood pressure is normal. Most people are going to be right in the 120/80 range. Right? Less and less people are going to be less than that. And then fewer and fewer people are going to be more than that. And I don't know exactly what the cutoff is. I think it's about, if you're over 140, over 100, they say you have high blood pressure. Right? It's about that. It varies depending on how old you are and your weight and all that type of stuff. But blood pressure is basically normally distributed. Right? So what that means is 68% of the people in this class would be within one standard deviation of a normal blood pressure. Now, we could have everybody within, which means it's even stronger than normal. Right? Yearly rainfall is normal. This year in New Mexico, we're definitely up here, right? We're definitely above average for rainfall. This has not been a normal year. We've got more than normal. You can determine the adequacy by comparing relative frequency distributions, and that's what we're going to do. And then it talks about some stuff that happens in 5.4, which we're not going to cover. All right? We're just covering 5.1, 5.2, and 5.3. So a lot of things are modeled by this normal probability distribution. Here's some examples. All right? So here's 3 examples of a normal symmetric distribution with different means and different standard deviations. All right? Different means and different standard deviations. All right? So, What the z-score does, which we've already talked about, right? In the first test, we made that z-score, that x minus x bar over s in that case because it was first sample. What the z does is basically takes all three of these normal distributions and makes them all look the same. It makes them relatively the same. That's what's nice about the z-score. So then we can tell things about the area under the curve. Right? So that's where we're headed. Now this big ugly formula right here is how you determine any y value, any f of x value based on x. So basically you say, well, when x is negative 2, what's f of x? Well, you plug it into this formula. All right? Now, that formula looks kind of complicated, huh? There's a lot going on right there. I would never expect you to do that by hand. Some you could do on your calculator. But let's read the very bottom of this. The probability of x is less than a is obtained from a table of normal probabilities. Thank goodness we don't have to do that every time, all right? We're given a table that tells us the probabilities based on a given x value. This is how you come up with any of the f of x values based on x. All right, so going back to that curve on the previous page, if maybe mu was 5 and this is 7, if I wanted to know exactly what this value is, what the f of x value is, I would plug in 7 into that big ugly formula. All right, and it would tell me. We don't have to worry about that, okay? I'm not testing you over this formula. You might have a question on your homework where you got to plug some stuff into it. Does everybody know that this is a number right here? E? E is a number. Yes, it is the exponential. Basically what E is, what it represents, it really comes from business mathematics, and that's the maximum compounding on a loan at any given time. You could never make more than 271%. That's basically what that's showing. If you take Math 113, we really get into an investigation of why that's the case. Math 113 and college algebra we talk about. You guys just need to treat it like pi. It's just some number. It's some letter that we've attached to some number. Now you'll notice E never shows up anywhere else in math. It's never used as a variable, right? It's never used anywhere else except for to describe this number. Euler's number. And Euler starts with an E. E-U-L-E-R. So that formula is really not very complicated. You just plug stuff in. It's not as complicated as it looks. You just plug in, you find sigma, find x, find mu. All right? Something you just put in your calculator. We have a table, though, that gives us the probabilities based on a given x. All right? Mu is the mean. Sigma is the standard deviation. All right? And then we have pi and e. Right. And this comes from the sine curve. This actually comes from trigonometrics, is why that 2 pi is there. If you guys have ever taken trig, you know, basically the circle comes back to the beginning after 2 pi. 2 pi represents 360 degrees. So that's where that comes from. Okay? Note that the mean and standard deviation appear in this formula so that no separate formulas for mean and sigma are necessary. They're given to you. To graph the normal curve, we have to know the numerical values of mu and sigma. Computing the area over intervals under the normal probability distribution is a difficult task. This is actually what you have to do down here at the bottom of the page. You have to do this integral. You have to integrate over the function. So that's calculus, right? You'll be given a table that tells you the area under the curve, all right? You won't have to go and figure it out. Consequently, we will use the computed areas listed in Table 4 of Appendix A. Nice. Okay, that definitely makes our life easier, learning how to use this table. Although there are an infinitely large number of normal curves, right, we could never write all of them because we could always find another mu and another sigma. No matter how many any of you picked, I could always find another one. Right? That's kind of the definition of infinity. Although there are infinitely many, one for each pair of values, mu and sigma, we have formed a single table that will apply to any normal curve. We call it the standard normal distribution. And it's based on mu and sigma. We have to come up with mu and sigma into the formula to get our z value. So the z table, the standard normal distribution, is a way of making all normal curves kind of the same. Okay? Right, and then there's the one for z. So notice right here they've replaced what? It was x minus mu over sigma. They've replaced it with z right there. We're not concerned with having to do that formula, all right? But this formula, if I was to graph this thing for z values from, say, 0 to 10 in some graphing calculator and hit enter, this is what the graph would look like. And notice here it's graphed from -3 to 3. And 0 is my mu. This is always the case with the z-score. 0 is always the mean. Okay, when z is 0, that means you're at the mean. Remember, the units on z, which we learned back in what, chapter 2. Z means number of standard deviations. 1 means 1 standard deviation above the mean. -1 means 1 standard deviation below the mean. So the unit of z is standard deviations. It's not feet, it's not inches, it's not miles, it's standard deviations. And the standard deviation changes depending on the problem. For this problem, it's 1. Okay? And you'll be given your mean and standard deviation. And then you just plug it into the z formula. Okay? Okay. The values for this definite integral can be obtained to any desired degree of accuracy by numerical approximation. For this reason, it is tabulated for the user. Right? If you want to learn exactly how to do that, then take either Math 124 or 215. All right? We get into talking about what an integral is. What does that represent? Okay? And integrals are, I mean, they're basically where the natural world, that's the foundation of how we describe the natural world, is through an integral. Right? Okay. The standard normal distribution, write this down, is a normal distribution with mu 0 and sigma 1. A random variable with a standard normal distribution denoted by the symbol z is called a standard normal random variable. Right? So z is the standard normal. Okay. The standard normal distribution is a normal distribution with mu 0 and sigma 1. So I'll leave that up for a second, and then we'll look at this table. So I might ask myself, what is the probability that z assumes any value between 0 and 1, between 0 and 2? Right? Over here, the probability that x assumes any value between 7 and 11 is 1/4. Right? And that's uniform. All right? Now, I didn't say that z assumes a range of values. I just said one specific value. Right? This is saying, what's the probability that z assumes any value, so in an interval between 0 and 1, or 0.5, or 0.4, whatever it happens to be. Bless you. So this chart basically has all the calculus done for us. These numbers in here were found by integrating that curve, by integrating that function that we saw on the previous page. Now notice what happens. What's the area under the curve between 0 and 0? Well, 0, nothing, right? That's one-dimensional. Now the way this chart works is in the left-hand column is either your first number and then your first decimal, and then you have a second decimal. So you can't find z values that are like z equals 1.357, because we don't have one that takes it out to 3 decimal places. All right. So what you need to do is you'd either find 0.36 or 0.35, and then try to find maybe the average between the two. What the heck happened here? All right. So the z-chart only goes out to 2 decimal places. All right? So I'm going to ask you this question. What's the probability that z falls between 0 and 1.35? Now notice I haven't told you anything about mu and sigma. That's how we come up with this number, is by plugging it into our z-score formula. All right? So let's just assume that we found the z-value. And I haven't even looked at the z-score formula yet today. We looked at it in the past. So let's see if we can answer this. So what's the area under the curve? That's another way to think about it. What's the area under the curve between 0 and 1.35? So the way we do it is we go and locate 1.3 in the left-hand column, which is what? Right here. And then we go over to the 0.05. So basically you're adding together the column and the row. Do we see that? So 1.3, 4, 1.35. There it is. The area under the curve between 0 and 1.35 is 0.4115. Another way to interpret this is basically there's a 41.15% chance that z will assume some value between 0 and 1.35. Okay? Now from this chart, I could even do z less than 1.35, and then I would just add 0.5 onto this, right? Because below 0 is half the curve. Does everybody realize that this is 0.5 down here, and up here is 0.5? Everybody see that? Half the area is left of 0, half the area is to the right of 0. So how much area is to the right of 1.35? What do you guys think? How would I find that out?
So multiply by 2.
Well, no, that's in between negative 1.35 and 1.35 is what you would do there. But I'm asking, what's the area? So here's my curve. You found it between 0 and 1.35. This area was 0.4115. What's the area right here? Or just subtract it from 0.5. Yeah, you could add 0.5 to this and then subtract from 1. Or since I know that half of this curve is 0.5, I would just take this away from 0.5. Okay? And we'll get a lot of practice doing this stuff, right? This is just my first introduction into it. So it's like 0.0885 is the area out here. So basically, I could find any area under the curve from this table. All right? Now, the table's in the back of the book. Z goes out to 3 standard deviations. This only goes out to 1.5 standard deviations. Because it's just an excerpt. It's just a small piece. Okay. What I want to do now is I finally located, now I know I've mentioned these before, but I located those old videos that I used to watch when I first took this class. Here we go. So you guys are welcome to go to this. It's called Against All Odds, which is kind of a pun on statistics, right? Against all odds. Kind of has multiple meanings. And look, it's got videos that go in and talk about everything we've covered in here. From what is statistics, to stem plots, to histograms, to measures of center, or measures of central tendency, right? Box plots, standard deviation, measures of variability, right? Normal curves, and then finally, normal calculations, right? So what we're going to do, I'm going to watch this video. It's about 12 minutes long, because I got to run over to duplicating and get some worksheets. But it talks about this club for tall people called the Boston Beanstalks. And how do they determine who's tall? Right? Well, what they do is they find the average height and then move 1 standard deviation above average, and everybody that falls above 1 standard deviation is considered tall. Right? And that's how they, and they do a z-score, and the video talks about a bunch of stuff. So it's a pretty neat video. I watched 90% of it. I didn't watch every bit of it. Hopefully it works. I worked in my office. kill the light.
Funding for this program is provided by Annenberg Lerner.
Can everybody hear that?
Hi, I'm Pardis Sabeti, and this is Against All Odds, where we make statistics count. Normal can be kind of a tricky term. Remember, its special statistical meaning has nothing to do with whether you're an ordinary Joe or a freaky oddball. In statistics, a normal curve is symmetric, single-peaked, and bell-shaped, and it's completely described by its mean and standard deviation. Normal curves have a unique feature that can be summed up by what's called the empirical rule. It's also known as the 68, 95, 99.7 rule, and here's why. About 68% of the observations will fall within one standard deviation of the mean. 95% will fall within two standard deviations of the mean. And 99.7% of observations will be within three standard deviations of the mean. The standard deviation is a natural yardstick for any measurements that follow a normal distribution. Take a look at the range of heights for all American women. Symmetric? Check. Single-peaked? Check. Bell-shaped? Check. The mean, mu, is here at 63.8 inches, and the standard deviation, sigma, is 4.2. That means the average woman's height is 5 foot 3.8 inches. We can measure out with our yardstick. One standard deviation from the mean in both directions takes us to 68 inches on one side and 59.6 on the other. So 68% of American women are between 4 foot 11.6 and 5 foot 8. Let's measure out another standard deviation with our yardstick. Now we're 2 sigma out from the mean in both directions, bringing us to 72.2 inches and 55.4 inches. That means 95% of American women are between 4 foot 7.4 and just over 6 feet. We can take it one more standard deviation out to 3 sigma. Now we wind up at 51.2 and 76.4. 99.7% of American women, the vast majority, are between 4 foot 3.2 and 6 foot 4.4. Only 1/3% of women, just 3 in 1,000, are out here at the extremes, shorter than this or taller than this. Life out at the extremities of a normal distribution can sometimes feel a bit lonely, hence the existence of the Boston Beanstalks. We dropped in on a recent get-together of this club for tall people.
If a person wants to join the club, we invite them to one of our social functions, and if we know they're coming, we have a tape measure ready. We put them against the wall, and we put a little mark on the wall and measure it.
Thank you.
The tape measure must read 5'10" for women and 6'2" for men to gain admittance to the Boston Beanstalks. These requirements make sure only the loftiest segments of the general population make it into the club. A member's first exposure to a tall club meeting can be quite a departure from the world these tall folks encounter every day.
Thank you, everybody. That was fun.
At the end of the night, my neck really hurt, and I couldn't understand why. And finally, I realized because I wasn't looking down. I was either looking even or up. I was the shortest person there because there was mostly guys, and they were all like 6'7", 6'8".
Instead of having the conversation be about a foot below me, where I couldn't hear it because of the music from the dance, I was able to talk to people.
In my whole life, I was always the tallest one, so I could see the entire room and everything around me. And for the first time, I had that feeling of the intimacy of a dance floor when you have people that are all the same height around you or taller than you. It was an amazing perspective change. And for the very first time in my life, I felt like I belonged in a group, like this is where I am supposed to be.
At the national average height for women of about 5'4", our producer was looking pretty shrimpy compared to the Beanstalks in attendance at this dinner dance. The club offers a convivial atmosphere where members can enjoy temporarily being in a place where they are of typical height and meet others in the same shoes.
Being in the grocery store and having someone ask you to get something on the top shelf, or, you know, it's always about reaching for something.
We actually have had members thrown off of planes because they couldn't fit behind the seats.
One of the members of the Tall Club has built his own house, and he has all of the counters about 4 inches higher than normal. He says that he used to have back pain all the time, but as soon as he put in the raised counters, he stopped having the back pain.
But overall, these Beanstalks are proud to be tall and love hanging out with their compatriots in the club.
It brings such a variety of people together in such a large group, and such an amazing group of people, that I can't recommend anything higher than trying to get into a group where you can be part of this. And for us, it's the Tall Clubs.
The minimum Boston Beanstalks height requirements are 5'10" for women and 6'2" for men. These standards seem at a first glance to be reasonable for a tall club, where members are aiming to socialize with the literal upper tiers of society. But just how far above the mean must one be to gain access to the Boston Beanstalks? If we look back at our normal distribution of women's heights, 5'10" or 70 inches is pretty far out here on the right. Statisticians can do more than simply eyeball it to say how far out our card-carrying Beanstalks are towards the tallest extreme of the height range. We can figure out what's called the standardized value of any observation. This value, often called a z-score, tells us how many standard deviations our observation falls from the mean, and in which direction. It's a way to convert data from a normal distribution into a standard normal distribution. Setting its mean at 0 and standard deviation at 1, almost all the data then falls between -3 and 3. In this case, the observation we're interested in is the 70-inch height requirement, so 70 is our x. We know from before that the mean, mu, is 63.8, so we can add that to our equation. And sigma, we know, is 4.2. Do the math, and we have a z-score of 1.48. Well, that's great, but what the heck does that mean? It means that a woman who just meets the minimum club requirement of 70 inches has a standardized height of 1.48, or 1.48 standard deviations above the mean. Z-scores can be negative too, if they represent an observation that is below the mean. How do the gentleman Beanstalks stack up against the general male population? Just plug in their numbers to the z-score equation, and we can see that the 74-inch requirement for membership is 0.98 standard deviations above the mean. A standard deviation of 0.98 is pretty darn close to 1. Think back to the 68, 95, 99.7 rule, and we can estimate just how much of the male general population is eligible for Beanstalk membership. 68% of heights are within 1 standard deviation. That leaves 32% of people further away from the mean. 16% are shorter than 1 standard deviation away, and 16% are taller. Based on our 0.98 z-score, we're approximating that 16% of American men are up to snuff in the height department, at least as far as membership in this club is concerned. But since we actually have a precise z-score, we don't have to estimate. We can calculate the percentile that's the actual cutoff for Beanstalk membership. There are 2 ways to do this. You can turn to a z-table, which lists how much of the distribution falls below any given z-value. In our case, we look up 0.98 by locating 0.9 for the tenths place on the vertical axis and 0.08 for the hundredths place on the horizontal axis. And that gives us 0.8365 as the proportion of heights that are lower than 6'2". In other words, 83.65% of American men are too short to join up with the Beanstalks, meaning 16.35% of American men make the cut, so to speak. That's pretty darn close to our estimate using the empirical rule. Alternatively, you can use software to calculate these percentages directly without using a z-score at all. What's helpful about z-scores is they allow you to compare observations from 2 different normal distributions, by standardizing them with a common scale. For instance, we can compare the eligibility requirements for male and female Boston Beanstocks. With the gents at a minimum Z-score of 0.98 and the ladies at a minimum Z-score of 1.48, we can see that the height requirements are actually more stringent for female Beanstocks. They're half a standard deviation further from the mean than their male counterparts. The height cutoffs are kind of a historical accident, left from when all the tall clubs around the United States joined together in the 1940s. But maybe it also helps keep the genders equally represented, since some women may be more motivated to hang out with taller men than vice versa. We can also use Z-scores to compute the percent of data that falls in the interval between two observations. Let's say we want to know how much of the American population is taller than I am, but still not tall enough to make it into the Boston Beanstocks. Basically, we want to know the percentage of area between 2 points. Calculate the Z-score for my height, 64.5 inches. It's 0.16, just above the mean at 0. We already know the Z-score of 70 inches, the Beanstalk cutoff. It's out here at 1.48. Looking at the proportions in a Z-table, I see that 0.9306, or 93.06% of American women, are shorter than the shortest Boston Beanstalk. I'm pretty close to the mean, with 0.5636, or 56.36% of women shorter than I am. Subtract the two areas, and you can see that this chunk, taller than I, but shorter than the club members, is 36.7% of the population. Well, I'm pretty sure that I stopped growing a long time ago, so the Boston Beanstocks is one club that won't ever accept me as a full-fledged member. For Against All Odds, I'm Pardee Sabetti. See you next time.
I want to mention that from her Z chart. So would anybody in here be a member? Mark, I think he'd be the only one.
Yeah. 6'2".
Okay, so because I'm like right at 6'1", so I wouldn't be a member either. But something I want to point out is look at her Z chart. Right there. So let's look at the difference between this Z chart.
The table.
Okay. What did ours start with when Z was 0? Remember, what was the area? 0. So what this chart does is it includes everything below your Z value. Okay, so what that means is there's basically two different types of Z charts that you'll see. All right? Her chart is the chart of this area. All right? So here's this. And then she has some value for Z, and it's all the area that falls below. So this is from the video. This is that chart. From the book, the chart in the book only gives the area from 0 to Z. Everybody see the difference between those two things? Right? So here, in this thing, whenever Z is equal to 0, right, in this Z-score table, we get 0.5, or half the area. Whenever we pull Z back to 0, and Z is right here, that means half the area is 0.5. From the book, when Z was 0, it tells us nothing because it's only counting the area above 0. Now you can still deduce all the same information that's here from this one, right? Because you just add 0.5 onto whatever you get here. Right? So it's still pretty simple the way it works. But you have to pay attention to what data you're given. Because you might be given both. And there is even some Z charts that do this. So here's my Z, and then here's the Z scale, and it tells the area above the Z. So every chart, it'll have this little picture listed above it to tell you exactly what area is being given to you. Okay? And let me show you from our textbook exactly what I'm talking about. That's a pretty neat video, though. It does a good job of explaining what the different stuff means. It does a good job of explaining what a Z-score represents. Does everybody understand what she said when she said that the women's height requirement was much more stringent than the men's? Right? Because the men's requirement was only 1 standard deviation above the mean, or 0.98, which is approximately 1. The female cutoff was 1.5, so it's even farther away from the mean. All right? So it had a lot less area. A lot lower percentage of people would fit the women's Beanstalk Club than the men's. All right? So let's go back to the book. And that's on page, what, 5 or 7, actually, not 5. Random numbers. Poisson. Here we go. 773 is where this chart appears. It's probably right here, too, on the page. Let's see. So let's go to 773. So notice how it has that picture at the top. That shaded region is the area that's included in the table. Does everybody see the difference between that and the one she had in the video, which was basically this one, right, that included all the area? Because for hers, when Z was 0, this number was 0.5, right? It was half the area. So that's what I wanted to point out there. Now, does the area less than 0, is it the same as the amount of area that's less than or equal to 0? Let me write this up in algebraic form. So when we're talking about continuous probability distributions, is the probability that Z is less than 0 equal to the probability that Z is less than or equal to 0? Does the endpoint matter? Is another way to think about this. No, it doesn't matter. Because there's no area at 0. These are equal. Why are they equal? Because the probability that Z equals 0 is 0. It's not like the discrete probability distribution where it could equal one number. The probability that it equals exactly one value is 0 because there's no area at one number. It's only one-dimensional. It has to be some type of interval. It has to have this inequality symbol. Okay? So I'm not adding anything extra when I say at 0 as well. All right? So this is an important point that I did not mention today. I know I said it on Thursday. Let's do a very important point. That or equal to has absolutely no bearing. All right? The probabilities are the same. So let's go look at some examples. Jump back to page 233. Okay. So let's do it. Using the standard normal table to find. So let's read it, and then I'll go back to the table and we'll answer this question. Okay. Find the probability that the standard normal variable Z falls between negative 1.3, and I don't know why they put a positive there. They should just write the number 1.33. Right? So because they don't put positive here, right? So if there's not a positive there, it is positive. You have to explicitly say that it's negative. So what we're asking for is what's the probability that negative 1.33 is less than Z, which is less than 1.33? So let's draw that. Let's see if we can draw this same thing up, all right? And see if we can kind of estimate it. So here's our normal curve. There's 0. There's 1 and negative 1. So right here is about 1.33, right? You guys agree with that? And then right here is going to be negative 1.33. So I want to know what the area is under the curve between those dashed lines. Everybody following me? What's the area between one standard deviation? Right, what's this area? Right, well, what's the area, the empirical rule, 68%? Or 0.68? Right, 68%, which is equal to 0.68, same thing. So this area between negative 1.33 and 1.33 should be greater than 0.68. Does everybody see that? Because we're adding on this little piece, and then we're adding on this little piece. All right? Now, I'm not sure exactly what the area is here, what the area is here. And thank goodness we don't have to do calculus for it. All right? Now, let me ask you another question. Is the area to the right of 0, is this area going to be equal to that area? Yes. Yes. This area and this area are going to be equal. So our chart only tells us from 0 to 1.33. So this is the one that Crystal said where we have to multiply by 2. Right? So we have to find what this area is, find what it is between 0 and 1.33, and then multiply it by 2. Right? So that's our method here, which is equal to 2 times the probability that z is less than 1.33 and greater than 0, of course. Okay? And I could say absolute value there, but I don't want to. So let's go to the chart. Oh, switch the caps. So 1.33 is our number. So we need to go find 1.33 on the chart, which is where? Here's 1.3, 1.32, 1.33 right there. So this is 0.4082, right? And this piece is 0.4082. So when I add them both together, I get the probability that negative 1.33 is less than z is less than 1.33 is equal to these two numbers added together, or 2 times 0.4082, which equals 0.8164. Which is definitely greater than 68%. And it should be less than the 2 standard deviation, which is 95%. So I know my value needs to be between 0.68 and 0.95, and it is 0.8164. These were supposed to be kind of brackets, but they didn't come out very well. Kind of like those ugly birds you used to draw when you were a kid, you know, you kind of put the wings. All right, so let's go look at the book and see what it says. 233. So there's our graph. Same thing I have drawn, right? So they call area 1 this yellow shaded region, and then area 2 this kind of purple shaded. Well, what's purple there? It's kind of like a light yellow in the book. All right. So it says here, in this example, we want to find the probability that x falls between negative 1.33 and 1.33, which is equivalent to the area between negative 1.33 and 1.33, shown highlighted in figure 5.9. Table 4 only gives the area from 0 to any positive value. So it only gives us this area. So what I need to do is double it. So we look up 1.33, the value in the 1.3 row in the 0.03 column, as shown at 510. So when we did that, we saw that it was equal to 0.4082. So the probability that negative 1.33 is less than z is less than positive 1.33 is equal to the probability that it's between negative 1.33 and 0, plus the probability that it's between 0 and 1.33. I'm not sure why they included that or equal to symbol there. So it's just A1 plus A2. I know each of these areas is 0.4082, so we come up with our conclusion, 0.8164. Now let's read the look back. Remember that less than and less than or equal to are equivalent in events involving z, because the inclusion or exclusion of a single point does not alter the probability because there is no area at a single point. Okay? So I can do this now for any z values. I can use that chart. These two things don't even have to be the same number. This could have been negative 2.5 and this could have been 1.7. Then I would just look up each of the areas and add them together. Because the area between 0 and negative 2.5 is exactly the same as the area between 0 and positive 2.5. That's why that chart only gives you the piece to the right of 0, because you can figure out everything else from that chart. Okay? So this says, find the probability that a standard normal variable exceeds 1.64. So let's draw, I want you guys to draw the curve and highlight the area it's talking about. And then I'll go back to the table. So we want to know the probability that our standard random variable is greater than 1.64 standard deviations above the mean. Let's go ahead and go in here and draw it. So this is 0, here's 1, here's 2, so 1.64 is going to be about right there. So does it want the area to the left of it or to the right of it? To the right, z greater than. So it wants this area out here. What's my area? Right there. All right. So what I'm going to do is I'm going to go to the z chart. I know to the right of 0 is how much? 0.5. So I'm going to find what the area is between 0 and 1.64. And then do 0.5 minus that area. So another way to write this is the probability that z is greater than 1.64 is equal to 0.5 minus the probability that 0 is less than z is less than. Everybody see what I have written right there? So the probability that it's greater than 1.64 is 1/2 minus the probability that it's between 0 and 1.64. I could say 1 minus the probability that 0 is less than, so I would include this half down here, but there's really no reason to. Okay? So let's go find this. This piece is listed in the chart, right? So let's go find the area at 1.64. So the area at 1.64, here's 1.6, right there. Everybody agree with that? 0.4495. So this is equal to 0.5 minus 0.4495, which equals 0.0505. Is that right? Is that what you guys get? 0.0505? All right. So what does that mean? Let's interpret that. That means this area is approximately, and I have to put approximately because all these values have been rounded. So the area is approximately 5.05%. So only 5% of the area, which this doesn't look like 5% because of my drawing, but it is. So the probability that z is more than 1.64 standard deviations above the mean is equal to 0.0505. Next page. And we'll get lots of practice with this stuff, okay? So here's a highlight of what we just did. Find the probability that a standard normal random variable exceeds 1.64. And notice as they go through, the standard normal is symmetric about the mean z equals 0. The total area under the standard normal probability distribution equals 1. That always is the case. So here it is. So the probability that z is greater than 1.64 is equal to A1. All right, they call it A1 because that's the picture they've drawn right there. So this is the area we're trying to find, which is the area I made you guys draw up. And I make you draw it before I show you in the textbook. So that area, I know from 0 and greater is 0.5, so I need to subtract off this area that I could find from the book, which was 0.4495, so my final answer is 0.0505. Okay? Now let's take some practice to really wrap your mind around, but once you get good at this, it comes pretty easily. And then you can even go backwards. I could say what z value corresponds to an area. Then you got to go in the chart and find that area, and then go find the z value that corresponds to it. Okay? So in 106, you do a lot of this stuff, but you're not really told why. Right? You're not really told, well, this is because it explains a certain phenomena. To attach some practical significance to this probability, note that the implication is that the chance of a standard normal variable exceeding 1.64 is only about 5%. Only 5% of the curve, or 5% of the area under the curve, is contained greater than 1.64. Okay? Let me see. I want to cover this next one. Yeah, there's lots of examples in this. Lots of examples. So let's do one more that is strictly less than. So let's look at this next example. So notice here, find the probability that a standard normal variable lies to the left of 0.67. This does not say between 0 and 0.67. This just says only to the left. So let's draw that. Let's draw that picture. Okay. So the probability that z is less than 0.67. So let's draw a picture that represents this situation. Notice I haven't bounded it below, right? There's no lower bound on z. Z can be negative 10 million, right? So I know here's 0 right in the middle. Here's 1. So 0.67 is going to be about right here. You guys agree with that? So it wants the area under the curve for any z value less than 0.67. So that's all this. Does everybody agree with my picture here? So the book only gives me from 0 to 0.67. But I know what it is from here, right? So the probability that z is less than 0.67 is going to be equal to 0.5, or half the curve. I know this is 0.5, right? Half of the area. So it's 0.5 plus the probability that 0 is less than z is less than 0.67. Because this part is given by the chart. See, this would be a situation where we'd want to use the chart that the girl had in the video. Because it includes everything. Yeah, question? No? So let's find this and add it to 0.5. So does everybody see that 0.5 is this area and this is that little piece right there? I'm just adding those two areas together. So this is equal to 0.5 plus. Now, how much area is between, what does the empirical rule say between one standard deviation? How much is in there? 68%. So what's in half of it? 34%. So I would expect this number to be less than 0.34, right? Because all of this is 34%. So I'm taking less area than that. So I would expect a number less than 0.34. Does everybody agree with me there? What I'm saying? Okay? So let's go find it. 773. And I'm definitely expecting a number less than 0.34. And it's always a good rule, a good way to kind of ask yourself, what value am I expecting as my answer? Right? What do I think is going to happen? And use that to kind of guide you. So at 0.67, here's 0.6. I don't go to 1.6, I go to 0.6. 0.6 and then go over to 0.7, 0.07. So right there. Is that less than 34%? Yes, so that follows along my model. So 0.2486. 0.7486. Or all of this red area is approximately 74.86%. Or basically, 0.67 is basically your upper quartile. That's why we wrote that number. Because remember, your quartiles are 25%, 50%, 75%. This number is dang close to 75%, right? 74.86. So 0.67 is essentially your upper quartile. Because 2/3 of the data lies below it, or not 2/3, 3/4 of the data lies below it, 1/4 lies above it. Okay? So this next one I'm not going to completely write out. I'm just going to kind of finger wave at it because it's pretty simple. So we can look at a more complex. So this says, find the probability that a standard normal random variable exceeds 1.96 in absolute value. So that means it's either greater than 1.96 or it's less than negative 1.96. Because the absolute value of all these z values is still greater than 1.96. All right? So this is really the first time we've looked at the word absolute value. Another way to think about that is, what's the area under the curve of all things that have a distance of 1.96 from the mean? Whether it's 1.96 above or 1.96 below. And notice how this is greater than, it's not less than. So that means the area greater than 1.96 and less than negative 1.96. Right? If this would have been flipped over, if this inequality symbol would have been flipped over, that would be this area in between 1.96 and negative 1.96. So basically all it is the areas on the tails is a way to think about it. It's the tails. And I call it tails because we're going to see that again in the future. One tail test, two tail test. It's basically testing for outliers. Right? Because you guys would agree that these areas, this is kind of where the outliers are, right? They're a long ways away from the mean. So it wants to know what the area is. So here's 0, 1. Let me put a dash line. 1.96, negative 1, negative 1.96. So it wants the area to the right of 1.96 and to the left of 1.96. So what they do is they find the area between 0 and 1.96 and then subtract it from 0.5 to get this value and then double it to get both. Okay, so this says the probability that the absolute value of z is greater than 1.96, right, is equal to the probability that z is less than negative 1.96 plus the probability that z is greater than 1.96. That's what it's saying. But it's really, since both these areas are equal, I can just say that's times 2, right? So it's equal to 2 times the probability that z is greater than 1.96. Because this area and this area are going to be equal. So I could just say 2 times that area. Which is equal to 2 times, so now this probability I need to switch around and put 0.5 minus the probability that 0 is less than z is less than. So the way to find the greater than piece is to take this area, which is between 0 and 1.96, and take it away from 0.5, which I know is half of this area, and then double it. So the main way to do these, the easiest way is to draw this picture. Once you draw this picture, you kind of have an idea of what's going on. Okay? Because the way this works is the chart doesn't just tell me each of these areas. I kind of have to remodel the way it looks so that I can cast it in a way that I can get the data from the table. Right? So to find this area, we do 0.5, which is everything over here, minus this piece from 0 to 1.96. And that'll tell me what this is, which will be what goes in the parentheses. And then I double it to get this area, because these two are going to be the same, because the normal is symmetric. All right? So let's go to the chart. Let's find 1.96. So here's 1.9. 1.96 is right there. 0.475. So this is equal to 2 times 0.5 minus 0.475. I'll just go ahead and put the 0. And this is 0.025, right? Equals 2 times 0.025, which equals 0.05. So this value is 2.5%, and this one, this area, is 2.5%. So how much area is between negative point? How much? 95%. And how do we find that? Well, if I know there's 5% that lies outside, or 0.05, I know all this area is 1. So that means in here is 95%. Right? And remember, our empirical rule said 95 at 2 standard deviations. It's because there's slight round-off error, but 1.96 is dang close to 1. This is how we produce a 95% confidence interval. Right, when we get to confidence intervals. Because I'm confident that 95% of my data lies between these two numbers. 2.5% lies below it, 2.5% lies above it. Okay? Let's look at our Z thing, which I've already talked about a lot, but let's go ahead and put a formal definition on it. Property of a normal distribution, this is the same thing we've seen a lot. If X is a normal random variable with mean mu and standard deviation sigma, so those two things have to be given to you, then the random variable Z, defined by the formula Z equals X minus mu over sigma. Now the one we saw from chapter 2, this was X bar and that was S, right? Because it came from a sample rather than the population. This is a population distribution. The value Z describes the number of standard deviations between X and mu. Okay. Now let's read this. This is the example we just did. It's right there on the board. Recall from example 5 that the probability that the absolute value of Z is going to be greater than 1.96 is 0.05. This probability, coupled with our interpretation of Z, implies that any normal random variable lies more than 1.96 standard deviations from its mean only 5% of the time. So this is kind of how we detect outliers. Only 5% of the data is above 1.96 and below 1.96 standard deviations from the mean. Okay? Compare this statement with the empirical rule, which tells us that about 5% of the measurements in mound-shaped distributions will lie beyond 2 standard deviations from the mean. Remember, in the empirical rule, it says this is approximately. Right? It says approximately 95% of the data lies within 2 standard deviations. And this really backs it up. Right? This is hard evidence that the empirical rule is correct. It's really 95% of the data lies between 1.96 standard deviations from the mean. Okay? The normal distribution actually provides the model on which the empirical rule is based, which makes sense, along with much empirical experience with real data that often approximately obey the rule, whether drawn from a normal distribution or not. So really, our empirical rule, it's off a little bit saying 95%, but that's why it always says approximately 95%. It doesn't say exactly, right? But we're going to see this 1.96 a lot because that's a 95% confidence interval. We're going to build 95% confidence intervals a lot. So Z is 1.96, okay? Then here's a cell phone one I was talking about. So I don't really want to do this one. I'm going to do a different example. We've got to go a little bit further. But it says here that the average length of time between charges is 10 hours with a standard deviation of an hour and a half. Which, I'd probably agree with that, right? Depends on how much you use your phone. If you don't use it, it lasts a lot longer than when you use it a lot. So it depends on what you're using it for. If you got your phone on Pandora for 4 or 5 hours, it really runs the battery down, right? Because it's constantly taking data in. It's constantly working. So this says the desired probability that the cell phone lasts between 8 and 12 hours, which is right around the mean, is highlighted. So what they do is they plug in 8 for x, they let 10 be the mu, and they let sigma be 1.5. So when they do 8 minus 10, that's 2 over 1.5. Well, 8 minus 10 is negative 2. So negative 2 over 1.5 is negative 1.33. That's the z-score. So we've already done this problem. We just hadn't had it casted in an example. Right? So 8 yields a value of negative 1.33. So 8 minus 10 divided by 1.5. Do that in your calculator and verify. But you have to do 8 minus 10 in parentheses. That subtraction needs to happen first. Or just do 8 minus 10, hit enter, and then divide by 1.5. And you get negative 1.33333 forever. Same thing when you plug in 12 for x. Oh, let's do a reverse. Good one. So that's on 239. So let's do a reverse z-table. Using the normal table in reverse. All right? Find the value of z naught. So that's a specific value of z. All right? Such that 95% of the standard normal z values lie between negative z naught and positive z naught. So what is my z value such that I produce that area? So we're going backwards here. We've been given z values in the past and had to find the area. Now we're given the area and we need to find the z value. But I'm going to do it a little bit differently because we've already done this one. I mean, we know the answer to this. 95% is 1.96 and negative 1.96. We just saw that. So let's do a different one. And this is strictly, neither one of these z naughts are going to be 0. All right? So what is z naught? And I'll go ahead and make it 0 just to make it easier to read the chart. So what's the probability that 0 is less than z is less than z naught? So find z naught or z sub 0 such that the probability that 0 is between 0, z and z naught, let me get one that I make sure we have. .46 0.71. So here's another way to think about it. I want to find Z. So what's Z naught such that this area is 0.4671? So see how this is going backwards? So let's go in the chart and find where this 0.4671 occurs in the chart. And really the only way you can do that is just by looking through it. Now notice all these are in ascending order, right? It always gets bigger. So I'm not going to look for 0.4671 back here. I'm going to go down here and look, well, here's 0.4582. It keeps getting bigger. Here's 0.4641. I'm really starting to get close. There it is, right there. So what's the Z value? Right. So this is the area. So the Z value is 0.184. So I'm going to erase Z naught and say 1.84. Now that example in the book, this wasn't 0, this was negative Z naught. So it was actually talking about the double area. So the way you'd have to do it is divide the area in half and then find the Z value, just like we did here. Right? So whatever the area is, if this number is not 0, if it's negative Z naught, which means it takes it out to this direction, just divide whatever the area term is in half, because I know half of the area will be to the right of 0 and half the area will be to the left of 0. So divide it in half and then do exactly what we just did. Right? Okay. 230. So here, let's look at this next. This is in reverse as well. 238. So let's answer this one. Find the Z values of Z, call it Z naught, in the standard normal distribution that will be exceeded only 10% of the time. So I want to know here what Z naught has exactly 0.1 of the area to the right of it. But the chart doesn't tell me what's to the right of it. The chart only tells me what's to the left of Z naught. So if 10% is above, that means 40% has to be below. So in my chart, I need to go find 0.4. Now, if there's not one that is exactly 0.4, we do the closest approximation. Right? So let's go look. This is just like the problem we just did, right? So what Z value corresponds to 0.4? So I need to get in the chart, find 0.4, 0.3980, that's really close. 0.4032. Which one of those two numbers is closer to 0.4? This one or the other one? This one, right? Because this is only 20 away here. This piece is 32 above. So it's definitely this one. So what I would say for the answer, you would put 1.27, which is actually a little bit more than 1.27. But this is as close as we can get using this chart. So if I go back to 238, oh, and then what it does is it says it goes above. So I'd rather go above than below. Oh, and you know what? I might have been cutting that off, actually. I was cutting it off. So I'm cutting off the 0.8. So where's this is dang close to 0.4, right? 0.3997. Sorry, I was cutting that off of the chart when we were looking at it before. So this number right here is the closest one to 0.4. Does everybody see that? So the answer would be 1.28 is what you would tell me. So a Z-score of 1.28 means approximately 10% of the data lies above it. right? And actually 90% lies below, right? The 0.5 below 0, and then the 0.4 from 0 to 1.28. Okay? Let's go look at a couple homework assignments. Now you can see why this section has taken, I even started it on Thursday, and I barely completed talking about it right now. So it's taken almost 2.5 full hours to talk about this section. That's how much is going on in here. All right, it's very important. So let's go look at, so notice 5.3 actually has 2 assignments. It has 2 separate homework assignments. All right? The 5.3a just deals with finding z-scores. It's pretty simple. And then the B and C is where you dive in a little bit further. Okay? And this worksheet I have right here. See this worksheet 3.13? Which that has to deal with a date, so I need to change that. That's 3.13. That's why that's there, because it was during the spring semester. But I'll hand this worksheet up. It's got 10 other z-score probabilities I want you to find. All right? So let's go in and look at a homework, and then I'll pass this out. Maybe we'll do one of these. Okay, so let's look at 5.3. Notice 5.3a and 5.3b and c are both due tomorrow by midnight, 6:30. Okay? So let's just glance at it real quick. So this is pretty straightforward. Look, it's only 3 questions, and the z-values are all between 0 and a number, so those come directly from the chart. We don't have any other manipulation to do, because it's from 0 to the right. So all we're doing there is looking at the chart. And notice this has the table right there. Okay? Now you're welcome to go use a separate table if you like the other ones better. The one from that shows up to z. Like, let me go online and find one. Because they all have the exact same type of data. Yeah, see this chart? This is like the one from the video. See how it shows everything from negative infinity up to z? And that one even shows below the negative values. But they all encapsulate the same amount, the same type of data, the exact same data. Okay? So there's that. So that's not too bad. So this one you just double it, right? Because our endpoints are the same. So you find it where z is 0.5 and then just double the area, right? With all these, go ahead and draw a picture, okay? And then notice here, it mixes the endpoints. So this basically says from 0.61 up to 2.41. So what I need to do is find the area from 0 to 2.41 and then subtract off the area from 0 to 0.61. Right? And there's, view an example, lots of help in the homework. So those are pretty straightforward. Here's where we got to go backwards. So this is where it's giving you the area, and you got to find the z-value that corresponds. All right. Part D looks kind of difficult too. Part D, there's kind of a lot going on right there. All right. So let's do, should we do it like that? Let's do that one actually, because that one's probably more difficult than any of the ones on the homework. Let me just glance at these. See, these are all pretty straightforward here. It gives you mu and sigma. In all these problems, you have mu and sigma. Okay? So let's do part D right here. So what I want to do is draw it first. Okay? So let's do part D. It says find Z naught. So here's 0, here's 1, here's 2. So I'm going to call this Z naught. Now how do I know Z naught is greater than 0? What's the area between 0 and negative infinity? What's all of this area equal to? 0.5. So if this area is greater than 0.5, I know this Z naught has to lie above 0. Right? It has to be over here somewhere. I'm not sure exactly where it's at. But I know it has to be over here because all of this area is 0.5. So I know from here, and that needs to be negative. So I need to find this area between negative 2 and Z naught. Now I know what the area is equal to. So I know this area equals 0.5348. Okay. So I want to know, so the chart is going to tell me two different things, right? It's going to tell me the area between 0 and 2, or 0 and negative 2, which is the same as the area between 0 and 2. So it'll tell me the area between 0 and 2 and the area between 0 and Z naught. Okay? So when I add them together, so the probability that negative 2 is less than Z is less than 0, plus the probability that 0 is less than Z is less than Z naught, has to equal 0.5348. Everybody agree with what I have written there? Take a look at it. Now this doesn't have any ambiguity to it, right? Like I can go into the chart and find this value. What is it? So what is the area under the curve between 0 and 2? Let's go look at the chart. I can't really zoom this chart in. See, it doesn't zoom. So let's go find 2.0. And I know it's really hard to see on here, but it's right here. 0.4772. So I know that this piece right here, this area between negative 2 and 0 is 0.4772. I'm going to put an implication there. Plus the probability that 0 is less than Z is less than Z naught equals 0.5348. So what I need to do now is subtract off that 0.4772. Everybody see that? So I'm going to write this same line on the next board so I don't run out of room. All right, so here's where I'm at. So I'm going to write this bottom line. That implies that 0.4772, which is the probability that Z lies between negative 2 and 0, plus the probability that Z lies between 0 and Z naught, has to equal 0.5348. I need to get this all by itself so that I can find the area that it encapsulates, and then I can go and find the Z value. So I need to subtract 0.4772. Over here they go away, so now I have the probability that 0 is less than Z is less than Z naught is equal to what? I didn't do that on my calculator yet. 0.5348 minus 0.4772. 0.0576. So now I need to go find the chart, look for the area that's equal to 0.0576, and then find the Z naught that equals it. So Z naught equals what? Let's go look at this chart. 0.0576. I know it's hard to see. Let me close that and go to the textbook. I hope it lets me go to this chart since I opened it in the homework assignment. No, See, it doesn't let me change the page number. I want to jump to the book. So I'm looking for the z-value that corresponds to 0.0578, or 05, was it 78? 76. 0.0576. Is it there? I did do that. 4772 at 2. Make sure I did that right. 0.4772. So when I subtract it from 0.538, 0.5348, did everybody come up with this number, 0.0576? And it's not quite in the chart. It's actually in between these two. Everybody realize that 0.0576 is going to be right in between them? Because this is 0.0557 and this is 0.0596. So 0576 is going to be in between. So I would say 0.145. Put 3 decimals on it. 0.145. Or you could even say between 0.415 and 0.14 and 0.15. All right, my area is right in here. So you could just add a 5 onto the 4 and put 0.145. Okay? So let's look at this worksheet. So this will be due tomorrow as well. But I'm not anticipating, everybody to be completely done. I mean, come in with some questions if you can't figure one out, and we'll work on it in class. All right? So it would probably be a good thing, did everybody get one? To go and print this page out of your textbook. Just go to page 773. And notice right here's the print button up in the top right. Print. Hit that. And I can't print off this computer, but make sure you don't, page 1, start with the current page. That's fine. Pay attention. Make sure you don't print every page from the textbook. All right? So just pay attention to what you put in. Because then you would use all of your pages. Yeah, I don't even know. Do you guys get 250 pages for the summer? Have you went and logged on? Have you noticed? Because I know each semester you're allotted 250 pages. All right? So, what I want you to do with these is draw a picture for each one. Draw a picture. All right? Really, the hardest ones on here are probably 6, 8, and 10. Are the hardest of those 10. All right? So draw a picture of what that represents. To try and kind of wrap your mind around it. You'll notice that I interchange the strictly less than and the less than or equal to. It does not matter which one we use. They're the same. Okay? So this assignment will be due tomorrow at the end of class. We'll kind of see how far everybody gets. Okay? My sign-in sheet's right here. Haley, you have hours this week?
Oh, yeah, they're 3 to 5, and they're probably 3 to 5 the rest of the semester.
In the alley?
Yeah.
Okay.
In the alley Monday through Thursday.
Okay. Monday through Thursday from 3 to 5. So that's right here, the basement of the Cub. Did they ever get that leak fixed? Is there a leak down there? No. Now, it might have been in the, it was in the cafe that was down there. But, okay, guys? So we've got a good idea of what's due. So there's 3 things to be working on tonight. The 2 My Math Lab sections, and then your worksheet. Okay? Thank you. Have a good day. question?
Yes, and this is from the homework that's due. Well,
The uniform
went
stuff?
over on Thursday.
Okay.
Does A and B equal meaning sigma?
No, A and B are just two other
Two
points
other
within, that are inside D and C.
Okay.
Yeah.
And then, let me see the other question. I guess I have
No,
to pull it up.
mu is equal to C plus D over 2. So B and C are just two numbers that are in between, or A and B are two numbers that are in between C. That's all.
Okay. And then number 7, I think I'm going to have to probably pull
What are we
up.
supposed to do?
Well, I should have probably made the note a little bit more.
A little more. Here. Well, you want to go to my office?
Yeah, that'll be fine.
Okay.
Because I didn't know.